Okay, we're going to start this contributive session. And the first speaker is Jorge Sanchez Segovia, and he's going to talk about high temperature partition functions and classical simulability of long-range quantum system. So.
Well, first of all, thanks to the organization for inviting me and giving me the opportunity of presenting this work, which couldn't have been possible without the collaboration and support of my colleagues, Jan from IFF and Alvaro from IFT. Let's get started. Basically, I guess that in this field, a lot of us, we are interested in spin lattice systems. And a common assumption to do when studying this kind of systems is that interactions are locals. Like, for example, in the async model, where you have nearest neighbor interactions. But why? Why do we assume this at the first place? Well, if you are a computer scientist, there are relevant computational problems that can be encoded in local Hamiltonians and a rich interface of methods between computer science and physics. If you are more into quantum simulations, there are efficient algorithms, both quantum and classical, that emerge thanks to the locality of the interactions. And in last instance, if you are a physicist, you know that generally atoms interact more with its nearest neighbor. But also, if you are a physicist, you know that electromagnetic forces are long range. So if we want to get a better picture, we must take into account long range interactions, as for example, Coulomb law, or dipole-dipole interactions, van der Waals. Well, the kind of system with this kind of interactions include Rydberg atoms, trapped ions, cold atoms and molecules, all of them, as we know, concurrent and promising quantum hardware platforms. And from a more fundamental perspective, it is also interesting that with these kind of interactions, there are some exotic quantum phenomena that cannot appear with local interactions, such as ensemble inequivalence or spin squeezing. So, I hope that we are all in the same page and motivated to study long-range interactions. And rather than focusing on a concrete model, we are going to try to study general properties of all these kind of systems. So we are going to do a pretty minimal assumption, that is that the interaction Hamiltonian between two constituents of the lattice interacts upper bounded by a power law on the distance, where alpha will be a free parameter that can be a positive number to study all the long-range interactions, the possible long-range interactions. And notice the following, that alpha parameterizes locality, because if alpha goes to 0, you recover an all-to-all interaction. And this is why from alpha equals 0 to equal to the dimension, it is called the strong long-range regime, where the long-range order is more strong, and you have therefore more exotic phenomena. But on the other hand, you have a mean field description to address it. In the opposite limit, you have of alpha going to infinity, you recover a local interaction, basically. And thanks to the assumption of locality, a lot of results, I'm not going to tell all of them in detail, have been, of general properties of local model, have been developed. And what about the intermediate regime, the weak long-range regime? Well, we expect some properties of local models to hold, but also for the long range to be important. But the thing is, the assumption is pretty more general, and it is more difficult to develop results with this assumption. And in the last few years, some of the results have been extended. I already don't know for local, but what we are going to try to do in this work is to extend this and to close this gap. So, well, I'm not going to bore you telling about all the results that are known in local and not in long range, but the important thing is that in local models, a lot of the results already known of the last years follow from analyticity of partition-like functions. I don't know if you remember those from your statistical mechanics course, but these kind of functions. And the thing is that if you are able to show that the Taylor series converges, then you prove analyticity. But in the context of quantum many-body, these objects are quite complex, and it is not trivial to show how this expansion can converge. So let's look at in the first place, let's look at it more detailedly. And notice the following, that as we are studying lattices, individual Hamiltonian terms can be corresponded with edges. And therefore, we can start using these graph theory languages. And notice that at this point, we will define polymers, which will be sets of connected edges, which are basically graphs, but you know. And each term of the and we notice the following, that each term of the partition function expansion can be corresponded to a set of polymers. So once introduced the language, I want to define our main technical tool, the cluster expansion, which is basically a Taylor expansion of the logarithm, but in the graph theory language. And it is called cluster expansion because we sum over sets of connected polymers. And yeah, and because this function here will vanish if not. And well, the weights encode the dependence on the inverse temperature and the traces. And the thing is, why suddenly the logarithm? Okay, the thing is that we are able to prove the analyticity of the logarithm, which is an easier quantity to work with. You prove the analyticity of the partition function. So we will try to prove the analyticity of the logarithm basically. And the thing is, how can we prove this? This is still not easy in the first place, but there are some mathematical physics who are almost like magicians to me, who developed this result that given any model, if this condition here, which is basically a sum over polymers connected to a certain site, if this condition is satisfied, then the logarithm is analytic and the cluster expansion converges. So thanks to them, the problem of counting sets of polymers gets transformed in a problem of counting polymers, so we are less screwed. And with all the concepts introduced, I can state at this point our main technical contribution, which is a theorem that we basically state that the Hamiltonian of long-range systems, if alpha is greater than the dimension, well, if this happens, the logarithm is analytic and the cluster expansion converges, meaning that if you expand the cluster expansion up to order m, the difference with the logarithm will decrease exponentially with m. So at high temperatures, this is satisfied. And I want to briefly sketch the proof without getting into the details, but for you to get to know what were the main technical difficulties to develop this work. And the thing is, well, we basically want to show this inequality right here, which is a sum over polymers connected to an edge, which can be closely related to a sum over polymers connected to a certain site of, well, this is an upper bound of the weight. So we want to control this sum, long story short. And the thing is, in local models, due to local interactions, these polymers cannot grow so fast. They have to grow, and if you have a fixed number of edges, the polymers are localized, and you have a finite region to find polymers, so combinatorics are quite easier. But in long-range models, this counting of polymers is really more difficult because you have an all-to-all connectivity, and this was an open problem in mathematical physics. And in this work, we noticed the following, that using the abstract tree root structure of the polymers, we are able to, and using long-range properties, we are able to do this counting. And we are able to prove the Kotechi price criteria. So now that the most technical part is over, you can all pay attention again. And basically, I'm going to explain why we bother ourselves in the first place to do all this mathematical physics stuff. And the first one is that we were able to get a classical algorithm for estimating partition function, which idea is really simple. Basically, we compute the cluster expansion up to order m, such that the difference with the logarithm is small enough. And with that, you get a sub-exponential algorithm, classical algorithm for this task. The thing is, the same algorithm for local models perform significantly more efficient because it's polynomial. So we observe here a great gap between local and long-range models. And let's compare it with other works. What's out there in the market? Okay, last year, also a classical algorithm with the same complexity came out. But the main difference is that it works only for one-dimensional system. In our case, it works for arbitrary dimensions. And it works, but on the other hand, it works for any temperature. And in our case, only for high enough temperatures. And more interestingly, also last year a quantum algorithm came out with a worse validity of alpha and of beta, but with a huge difference in complexity because it's polynomial. This raises up the question of, is there quantum advantage for doing this task? Well, now leaving algorithm aside, I want to focus on more fundamentally physics properties. And well, mainly into statistical properties, because as we know, quantum physics can be naturally described with probability theory, and this is an especially useful approach in quantum many-body systems. As we all know, if given an observable A, the distribution of probability of this observable is given by this one with this kind of moments, and there are these really cool functions which are the moment generating functions that notice that are really like partition-like function actually, like the ones we work with, and by approximating them, you can get a lot of really interesting probability theory results, and with our theorem, we can control it. So basically, by controlling these functions, we were able to show that ensemble equivalence has to hold if you are in the weak long-range regime via a bound. I won't enter in the details. And also, other important theorem that we were able to show is the variation theorem. For those of you who know, it's like a stronger version of the central limit theorem. And the thing is that given a quantum state, either gives a state at high enough temperature or product state with a non-arbitrary or weirdly small variance, which is almost always the case, the difference between the cumulative distribution function and the cumulative Gaussian function, the maximum difference decreases with system size. So the take-home message is that the distribution of any observable in this kind of systems will require a Gaussian distribution when the system with the system size is high enough. And we tested for a especially interesting case, which is the Gaussianity of the density of states. This quantity introduced in a lot of condensed matter courses, and we studied with tensor network numerics for a concrete model. The long range is in chain, and we plot here the error, which is the difference between the Gaussian fit and the numerical estimation. At what we appreciate is that if we increase locality, or aka alpha, the error decreases, so Gaussianity increases with locality, and also that Gaussianity increases with system size if you are not in the strong long-range regime. So coherent with our analytical results. And also I want to talk about the implications of our results in terms of for critical phenomena. And the thing is that if this function right here is analytical, like the one we've studied, it also implies the analyticity of the Loschmidt echo. Therefore, there will be no dynamical quantum phase transition at short times, for those of you who know what are those. And the analyticity, and also implies the analyticity of the partition function, so therefore there will be no thermal phase transition above the threshold. And finally, I want to introduce a last type of phase transition that we were able to constrain, which are excited state quantum phase transitions, which are basically singularities in the density of states that indicate a qualitative change in the excited state spectrum. We have a lot of less knowledge of this kind of transition in comparison with quantum phase transitions. To illustrate the concept, at left, we have a quantum phase transition, which is a crossing of level when varying the control parameter of the first excited state and the ground state. And in the excited state quantum phase transition, you observe the same phenomena, but in the excited spectrum realm. And the thing is, this kind of transition have been found in all models where you have collective symmetries and a semi-classical limit. But when you don't have that, there is no way to find them, and there is the open problem of can they even show up? And we tackle this and with our results we can tackle this question, because from the variation theorem holds the Gaussianity of the density of states, which in the thermodynamic limit becomes a delta function, as can be observed also in the numerics, that when you increase system size, the density of a state gets sharper and sharper, even also for alpha smaller than the dimension. So we conclude that as you only can have this kind of density of states, SQPTs are heavily constrained, and unless you have some special symmetry, so we conclude that it's a phenomenon that you can only observe in really special systems. And so to conclude this work, basically we were able to show that in the weak long-range regime and also in the local models, they have common statistical properties and an absence of same time of criticality because partition functions behave similarly. And we hope that this work can be useful for extending more results of local models, because we were able to give this tool, which is the cluster expansion, which has been useful in the past to get a lot of results. But the main difference is with local models is for estimating partition function classically, a huge difference in complexity. And also another question that raised up of our work is if there is quantum advantage for the task of estimating partition function at high temperature, which likely means that there is simply more work needed to do in classical algorithms. So with that, I want to thank you for all your attention. And if there is any question, don't hesitate. And thank you.
Okay, thanks for the nice talk. We have time for a very quick question. Someone? No? Okay, I have a very quick question. Maybe I missed, but are your results also valid for the strong long-range regime? Or why is this more difficult?
Yes. Well, the main reason, I think I have some backup slides that to make an intuitive why our work do not hold in the... sorry. Well, the thing is that our result only work in the weak long-range regime. This is something that we could expect from more phenomenological, in some sense, works that we had seen. But from a more formal point of view, which is the, well, more of our work, basically the thing is that the threshold temperature there, you have this quantity, which is U, which is basically a sum, which is, well, I will, is there, well, if not, I can say it with works. I don't know if, oh. Okay, yes. Basically this quantity is, well, you have your lattice, and you have all these sites which are at a fixed distance, and the number of sites at fixed distance d grows as the surface. So the thing is, that quantity right here that appeared in the threshold is a sum over all the sites with fixed distance, and as you can as you can see right there, this series, because of the growing with surface, will only converge if alpha is greater than the dimension. So that's why. Yeah.
Okay. Thanks. Here's the speaker again, please. So, our next speaker is Carlos Fulgado Claudio, and he's going to talk about entanglement cones and horizons in analog cosmological production of the Dirac fermions. So,
thank you. Okay. Okay, so thank you very much to the organizers for giving me the opportunity to share my work. So I'm Carlos Fulgado Claudio, and I will share with you a bit of an overview of the work that we have been doing. So it's done in that paper mainly with Alejandro Bermúdez, and it's also based on previous articles. Okay, so first I will start from the very beginning with the motivation. So as you know, quantum field theory is a framework that allows to describe phenomena at widely different energy scales, so ranging from graphene. Also, it can explain the physics happening in the LHC. Okay, so it's a very powerful tool that we have. Traditional QFT assumes Poincare invariance, so it means that the quantum fields are assumed to be living on a flat space-time, so on Minkowski space-time. Okay, with this description, quantum field theory is able to explain 3 out of the 4 forces of nature that we know, so ranging from electromagnetic force, strong force, weak force, but it fails to explain gravity. Okay, so, well, we are facing this problem, so there are several approaches to solve this. The first one, and the perhaps more ambitious one, is to define or to create, to make a quantum theory, or a theory of quantum gravity. Okay, we had this nice talk by Carlo Rovelli, who is trying, but this is hard, this is very hard. Okay, we still do not have a fixed theory of quantum gravity. So in principle, well, this would prevent us from knowing how quantum fields relate to gravity. However, there are less ambitious alternatives. For example, this quantum field theory in curved spacetimes, which is kind of a semi-classical approach that assumes that the fields are quantum, but the spacetime is classical. So it only requires modifying the description of the quantum fields, promoting the Poincare invariance to a higher symmetry group. An example of this semi-classical approach is this Einstein equations in a semi-classical form, where the left-hand side is purely classical, while the right-hand side containing matter is quantum. So we take the expectation value. Okay. This approach, let's say, to the problem of not having a quantum theory of gravity is relevant for a number of reasons. It's relevant because it is expected to be valid and to be a good description of reality for energy scales well below the Planck scale. So it's relevant for a lot of cosmological situations. It's also interesting because it contains a lot of effects that do not have a flat space-time or a classical counterpart, such as the Hawking radiation that you might know. And it also poses interesting questions connecting different areas of physics. Okay, so I mentioned here the information paradox and the relationship between entanglement and gravity that I will tackle a little bit in a few minutes. However, this is still difficult to approach, mainly because you need to compute the expectation values of quantum operators and its time evolution. Gravity requires studying dynamics, so this is something that is typically difficult to compute. What one does usually is to use Feynman diagrams. That would be the first approach, but this is problematic in some situations because Feynman diagrams are a perturbative expansion, so it's no longer valid if your theory is, for example, strongly interacting. So for strongly interacting theories, we cannot rely to Feynman diagrams. An alternative, this also happens in non-gravitational situations, for example, in QCD. So an alternative is to use classical simulations, such as this lattice QCD approach or Monte Carlo. But these also have problems, such as the exponential scaling, with the dimensionality and with the size of the system, the same problems when trying to simulate fermions, and also the inefficiency for real-time dynamics, which is vital for gravity. Okay? So an alternative to this is to use quantum simulators, which overcome all of these problems. For example, fermions are implemented physically in the experiments, and real-time dynamics is also very, well, I won't say very easy, but it's feasible to simulate. Okay, so the resulting picture would be something like this. So we have on the one side gravitational physics. I put here this picture of the black hole, where quantum fields are having some sort of relevance, and this is mapped to a quantum experiments involving, for example, in this picture, neutral atoms in optical lattices. Okay, this is the mapping. Okay, so with this in mind, I will explain to you an example of how this can be applied to a specific phenomenon. So I will mention the phenomenon of particle production, cosmological particle production. This, well, I will describe it very quickly. If you start with a vacuum state, but you are in an expanding universe, the pure expansion of the universe induces the creation of pairs of particle and antiparticle, let's say. So it's just the evolution of the universe that excites these pairs of particles. Okay, we will study this phenomenon for Dirac fermions, which are hard to simulate classically. We will assume for the moment no back reaction, which is just an approximation. And we will consider this expanding universe, which can be described by this line element. As you see, this is an increasing function. Okay, the resulting action, and I will skip the details, can be written as this. Okay, and this is just how you describe fermions in an expanding universe. It's all encoded in the mass. Okay, this mapping that I was proposing you, we show that in our articles that this system of fermions can be mapped to an experiment of cold atoms like this, subjected to optical lattices. Okay. Again, I will skip the details, but I want to mention that the Hamiltonian of these experiments is a lattice Hamiltonian, and I will stress the fact that this Hamiltonian contains this term, accounting for interactions, which you can control via phase-back resonances, so you are not limited to the perturbative regime. You can study more complicated situations. Okay. So the typical observable in quantum field theory in curved spacetimes is the spectrum of production when studying this phenomenon, which basically tells you how many particles are excited for a given momentum. Okay, so you have resolution in momentum space. You can measure this in the experiment by means of path mapping techniques, and you obtain plots like this. I want to stress the fact that you do not have spatial resolution. You only have resolution in momentum space. This is something that we will try to overcome in our work. Okay, so now, well, this was only for free Dirac fermions. This can be also solved exactly numerically. This is very easy to simulate classically. So we will now go to some questions that you cannot answer classically. So you would resort to a quantum simulator. Okay. So I will answer in this presentation 2 main questions which are open. The first one is how do non-perturbative interactions modify the well-known free results? Is there any regime where the interactions induce some interesting phenomenon? And the second question is how to gain spatial resolution, and is this interesting in any case? Okay, these are 2 questions that I will try to answer in this presentation. And to answer them, I will use 2 concepts taken from the quantum information community. The first one is the quasi-particle picture, and I will explain it in a little bit more detail in the next slide. And also the entanglement contour, which is an entanglement measurement that I will also introduce now. Okay, so first, I will explain the quasi-particle picture. So these produced particles that are produced gravitationally are created in pairs which propagate in opposite directions. So this is something like this. When they are created, these particles are entangled and they start to propagate, so they start to spread entanglement. Entanglement grows and spread as a consequence of the propagation of particles. The quasi-particle picture suggests that the growth of entanglement is only due to the propagation of these quasi-particles. So it says basically that other sources of entanglement, such as vacuum entanglement, are negligible compared to the propagation of particles. Okay, in this situation, we can map the propagation of entanglement to the propagation of quasi-particles, let's say. Okay, so there's like a duality, let's say. The next concept is entanglement contour. As you know what is entanglement. We can have a system like this blue line. We make a partition and we can compute the von Neumann entropy, which is called the entanglement entropy. It's just a number that tells you how much entanglement is there between the partition and the environment. However, this is just a number and you do not have any spatial resolution. So the entanglement contour is a function that is normalized to the entanglement entropy, but it has values over the partition. So a larger value of the entanglement contour, for example, in this case, means that that point of the partition contributes very much to the entanglement of the overall partition, let's say. While, for example, the middle in this case is disentangled because the value of the entanglement contour is 0. This just reflects the area law. Okay. So if we take this concept, which brings spatial resolution, and include the quasi-particle picture or go to that regime, we go to a situation in which just by studying the evolution of entanglement contour, we can have spatial resolution over the production of particles, or the particles that are gravitationally produced. Okay, so just to test the quasi-particle picture for the situations that we study, this is the prediction, the analytical prediction that the quasi-particle picture offers, and this is our numerical result. So you can see this is not the same picture, so but it's a very good. There's a very good agreement between both of them. Okay, so we can go and believe the quasi-particle picture and understand that there's a mapping between it and the propagation of particles. So now I will try to answer both of the questions that I mentioned before using these concepts. The first one is how do interactions modify the results that we know? So one effect of strong interactions is spontaneous symmetry breaking. Okay, in this model where there's an interaction among fermions, 4 Fermi interactions, there's a breakdown of parity. Okay, so it constitutes the so-called Aoki phase, and if interactions are strong enough, parity is broken, meaning that particles propagating left and right are not equivalent, let's say. Okay, this obviously also affects the entanglement contour and its evolution, meaning the evolution of quasi-particles. And this is a picture. Well, each of these figures can be understood. You can think of those as a spin polarization of the Dirac fermions, and you can see that in each of them there is an inequivalent flow to the left and to the right, meaning that the parity has been broken, and therefore we can see here directly in a figure that particles adopt this symmetry breaking, let's say. There's a higher symmetry that makes that both pictures are one the reflection of the other, but parity is broken individually. Okay. So this answers the first question. With these tools from quantum information, we can tackle, we can study the effects of strong interactions. The second question is, why would we need spatial resolution? Since we are in a gravitational setup, let's say, I want to see something equivalent to the cosmological horizons. When the universe is expanding, a very natural concept is this of horizons, and there's one called the particle horizons, which basically defines causally disconnected regions, meaning that if there's a particle that is expanding and traveling away from me faster than my maximum velocity, I will never be able to send information to it, and therefore these cannot share any kind of information. They are causally disconnected. Well, obviously, they are causally disconnected. Correlations go to 0, and entanglement cannot cross that horizons. We can also see this in the propagation of entanglement contour. This white region is the horizon, and you can see that these cones that I showed before, now when the universe starts to expand, bends when they approach the horizon, and they keep stuck. So entanglement cannot cross that horizon, and this is something that you can only see if you have spatial resolution. You could not understand this in terms of entanglement entropy and its evolution. Okay. So with this, well, I will just mention quickly the conclusions, or at least the way we think about this stuff. So we can quantum simulate cosmological scenarios, which allows us to perform very difficult computations, let's say, and to access regimes that are not easily accessible. Once we have this, we can use quantum information tools to analyze the results that we obtain. With this, we can learn new stuff and hopefully find new phenomena combining all these fields of study. So with this, I thank you.
Okay, thanks for the nice talk. We have time for some questions. Don't be shy. No? Okay, so I want to ask you a question. I think I have showed you in the second slide the metric, or well, the BS. I mean, or one of the first, a bit well, much more, a bit more, more. It was with the well, it's not a. I know. Let me. Yeah, sorry. I mean, it was not the second slide. Okay. I mean, yeah, it was. To the metric side. This is like a 1+1 dimension model, no? Or some, so, is there a reason to do it in 1 by 1? And it's for well, each one.
Yeah. There is no reason. You can, in the quantum simulator, you can generalize this to any dimension, well, 1, 2, or 3 dimensions. The reason that we study just 1 dimension is precisely because these results that I was showing you, they are performed classically. So they are not taken in a quantum simulator. They are just a Gaussian approximation of the results. And this is much simpler in 1+1 dimension. And this motivates the necessity for a quantum simulator to allow us to go to higher dimensions without an exponential scaling of the computational cost.
So let's thank the speaker again. Okay, so our next speaker is Álvaro López, and he's going to talk about Bose-Einstein condensates as relativistic quantum information simulators. So the floor is yours.
All right, thank you everybody for being here, and thank you, I would like to thank the organizers for giving me the opportunity to tell you today a bit about, or to give you some ideas of the potential of Bose-Einstein condensates for simulating quantum fields and for studying relativistic quantum information related questions in the context of field theories. So the first idea that I want you to know is that quantum fluids allow us to simulate the dynamics of quantum fields. This could be done in curved spacetime, so we can simulate the dynamics of fields in curved spacetimes, but this is not the only interesting thing. So in Minkowski, this would be also interesting. I will go to that later in the talk. And the reason behind this is that fields propagate on top of some background in the same way as perturbations propagate on a fluid. If we have some quantum fluids, then we would also expect that some aspects of quantum fields can be reproduced in these kind of systems. And some examples of platforms where you could realize this kind of dynamics are polariton fluids, superfluid helium, but I will focus on Bose-Einstein condensates today. And in particular, you can try to simulate quantum fields on top of some cosmological space-time. And the way in which the analogy works in this case is the following. So let's say that we have some Bose-Einstein condensate. So most of the atoms are in the ground state. We have a weak interaction between them. So we are going to have some small perturbations on top. And when you study the motion of those perturbations, you realize that these can be described by some sort of effective metric that depends on the properties of the ground state, so the properties of the condensate. If you tune in your laboratory, if you tune the properties of the ground state, you can engineer this metric to be that of a cosmological background, and therefore you realize that your fluctuations, your phonons propagating through the condensate, behave as massless scalar particles, in this case, in a cosmological background. So I will start with that. So let's see how these phononic fluctuations actually behave as scalar fields in curved spacetimes. And for this, I will focus on a 1+2 scenario because I have a particular setup in mind that's a disk-shaped condensate, very tightly confined in the side direction, if you want. So we are going to study the motion of the fluctuations on top of the condensate, and let me make some assumptions. So first, let's assume that the excitations, these fluctuations, are so have low energy. That means that we are in the acoustic regime, and these actually behave as phonons. And then I'm going to also assume that the background density profile of the atoms in the ground state is stationary, so the condensate doesn't change its size whatsoever. Now, when you look at the field that describes these phononic fluctuations, you see that the equation of motion and these assumptions can be written in this very simple form, and it depends on the speed of sound in the condensate. This is precisely the speed with which these fluctuations propagate. You can rewrite this in a very clever way and write it in terms of this g mu nu, which is going to be our effective metric. And with these, you realize that your fluctuations actually can, well, they have the same dynamics as a massless scalar field in some geometry given by this metric, which depends on the properties of the background. So essentially, as I was saying, depends on the speed of the phonons, which is given by the interaction strength or the scattering length of the condensate, so the interaction strength between the atoms in the ground state, their background density profile, and the mass. Now the question is, can we tune this, can we adjust these parameters to make this metric look like a cosmological metric? And the short answer is yes, we can engineer these kind of cosmological spacetimes. And long story short, if we change the density profile of the atoms in the ground state of the condensate, we can engineer the different types of spatial curvature of cosmological spacetimes. And the expansion rate of the universe is implemented by changing the interaction strength. So when you look at the metric and you look at the function that describes how these spatial slices are expanding, you realize that it's given by this combination. It essentially goes like 1 over the interaction strength. So if you are able to decrease the interaction strength in your condensate, then this is going to, well, it's going to be equivalent for the phonons to expanding the universe in which they live in. Now note that I said that the condensate doesn't change its size, so what's actually happening when we expand the analog universe in which these phonons live, it's not like the condensate itself is expanding, but really the speed of sound is decreasing, and from the point of view of the phonons, it looks like it takes more time to cover the same distance in the condensate. So it's just another way of looking at the expansion of the universe. And as we just saw, one of the phenomena that is natural to quantum field theories in expanding backgrounds, but really to quantum field theories in the presence of some external field, for example, also if you have some external electric field, you would have this kind of per production, that would be the Schwinger effect. But this, in particular, this cosmological or gravitational per production due to the expansion of the background is a very interesting mechanism that happens in this kind of cosmological setups, and it's actually the responsible for the amplification of the fluctuations of the inflaton field in the early universe. Now, when we do this kind of analog expansion in our condensate, we are going to see something very similar. So these are actual pictures from an actual condensate. And when you perform this decrease in the interaction strength, some fluctuations are going to appear in the condensate, and you can relate this to pair production or pair of mode production. So these are going to be really pairs of phonons that are going to be produced in the condensate. So I don't want to say too many things about this cosmological pair production, but one thing you could do, moving to the information part, is to study what's the entanglement between the pairs of produced particles because of this expansion. The way in which this would be done in this kind of experiments is by measuring the density contrast of the condensate. So by measuring what's the total density of the condensate with respect to the background density, you can extract the fluctuations in the density, and these these correspond to these phononic perturbations. And in this way, you can then extract the correlations between the density contrast for every pair of points in the condensate. And this allows you to reconstruct all two-point functions for your field. If your state is Gaussian, which is what we assume, then with this you can actually know what's the full quantum state of your system. And once you have the full quantum state, you can then build entanglement observables. For example, you could build this kind of Cauchy-Schwarz inequality and make some theory predictions of what would be the feasibility for detecting entanglement in these kind of setups. Now, this is a theory prediction where we are plotting the Cauchy-Schwarz inequality as function of the wave number of the pairs of modes produced for some pretty conservative, I would say, but reasonable values for the experimental parameters associated with the experiments that we already did and we already know. And essentially what we get is that right now, current technology would allow us to detect entanglement with significance between 2 or 3 sigmas for these produced pairs. And lastly, another idea that I want to give you is that, okay, these platforms have been used for simulating quantum fields in curved spacetime, but this does not need to be the case. Quantum field theory in Minkowski spacetime is still interesting. So even if we forget about the analogy with cosmological spacetimes, there are many things that we could do for exploring the information structure of quantum field theories with these kind of setups. And we could study, for example, what's the spatial entanglement between different regions in our condensate. So you can think of a configuration like this, well, in 2D, if we have the condensate that I just mentioned. But essentially, what's the entanglement between modes defined on a ball and on a shell? And then we can make similar predictions for, now this is, for example, logarithmic negativity, which is another entanglement observable that you could build out of your covariance matrix, and then make some predictions for what would be the detectability as function of the temperature of the condensate in this case, and again, for some reasonable values for the experiments. So I just wanted to give you some ideas and convey that Bose-Einstein condensates are a very powerful tool for simulating quantum fields, not only in curved spacetimes. We could, for example, prove cosmological pair production, but it's also very interesting to explore relativistic quantum information related questions, and this does not need to be done on curved spacetimes. The theoretical community that works on these topics have been exploring these ideas also in Minkowski, and there are many things to do, so we are pretty excited about it. And just I wanted to quickly mention the people that worked on this quantum field simulator, not all the time, but along several small projects and so on, and also the people that did this relativistic quantum info analysis and so on. So yeah, that's it. Thank you.
So, fine. Any questions? Okay.
Thank you for the talk, and sorry for the naive question. Has this analog metric anything to do with this quantum metric and so on, in the sense of geometrical metric in quantum systems?
So I don't know if you, okay, so the way in which this metric emerges, so it does not come from Einstein's equations. I don't know if your question goes in this direction.
The quantum metric of, for example, the ground state of given quantum system.
Okay, so I don't think this is related. So really what's happening is that I am rewriting the equation of motion for my fluctuations, and I call some terms metric because then I am able to reproduce the dynamics of fields given by that metric, but there's really no space-time origin for that metric, if you want. So it doesn't come from any, let's say, it doesn't come from the structure of the geometrical structure of the condensate or the system or whatever. It does not come from Einstein's equation. We are really just simulating the dynamics, so the equation of motion of the field, just by renaming, if you want, naively, renaming some terms and calling whatever metric, because then it looks like the dynamics of the fields. I don't know if that answers, but okay.
Okay.
Hey, thank you for the talk. I have a quick question of the last graph, in which I don't know if I got it correctly, but does the entanglement enhance at some point with the increasing of the temperature?
Sorry, can you say that?
Like you see, like when you increase the temperature, that's some point where the entanglement grows. And is this that, I don't know if I'm getting correctly, like the graph.
Yeah, so entanglement is very sensitive to temperature, and at some point when you keep increasing the temperature of the condensate, in this case, then it will just vanish. So it's not like it's kind of a noise. It can really destroy all the entanglement between the regions. So yeah.
Okay.
And an interesting thing that we can see here is that at some point decreasing the temperature is not going to increase the amount of entanglement that you see. So the way entanglement behaves, at least for me in this kind of setups, it's not, let's say, very intuitive, right?
So temperature destroys the disentanglement always.
Sorry?
Then this temperature always destroys.
Yeah, it always goes against entanglement, yeah.
Thank you.
So, any last quick question? Okay.
Thank you for the presentation. I guess I found your first answer to that question over there slightly confusing, because you said that the metric that you're working with is not related to the geometry of the problem. But however, it was related to the speed of sound in the Bose-Einstein condensate, and in principle you assume it to be inhomogeneous. I mean, in some certain sense, wouldn't it be related to the geometry?
It depends on what you understand by related with the geometry. So the point is that we are not simulating GR plus some quantum field on top. So the field equations for that metric are not Einstein's equation.
Right.
It comes from the ground state equations, which would be Grosby-Daevsky in this case, and whatever happens then, and we just rename the terms. But so in this sense, of course, it has to do with the properties of the ground state. If you change, so the properties of the condensate, if you change the interaction strength, if you change the speed of sound, this is going to affect the equation of motion of the fluctuations, which can be recasted in the form of, or in terms of some effective metric. But the background equations for that metric are not Einstein's equations. That was just my whole point.
Right, yeah. Okay, thank you very much.
Okay, so let's thank the speaker again. Okay, so our next speaker is Carlos Barona, and he's going to talk about time-delayed dynamics in waveguides, greedy, and bosonic quantum networks.
Okay, well, first of all, I wanted to thank the organization because I think they're doing a wonderful job during this conference. And well, now for the next 10, 15 minutes, I'm going to be talking a little bit about the work that I've been developing in this first stage of my PhD in a collaboration with some other members of the group QINFOC here at the Instituto de Física Fundamental. We have Juan José, who is my PhD director, and some collaborators, Alan Costa and Hong Yang. To kick things off, I wanted to give a small introduction to waveguide quantum electrodynamics so that we all know what system I'm referring. In order to understand it, we need to understand its two main ingredients, which are, of course, the waveguide and the emitters. The emitters are the quantum bodies whose dynamics we're interested in. In quantum technologies and quantum computation, we typically want to consider two-level systems because they represent qubits. However, other types of emitters may and will be considered, like, for instance, linear emitters, which corresponds to cavities, which we then couple to the waveguide, which is this second ingredient, which is represented by this blue cylinder here. And you can think of a waveguide as a cable that supports one-dimensional modes of the electromagnetic field. So as a whole, what we have is an array of emitters, which is coupled to a bath of one-dimensional modes of the electromagnetic field. These two ingredients, as simple as they sound, already encapsulate a very high degree of complexity. So in order to obtain some analytical results, one typically needs to do a series of approximations. One of the most common approximations is known as the Markov approximations, which basically states that the time scale in which the dynamics of the degrees of freedom of the electromagnetic field happen is much shorter than the time scale in which the emitters evolve. This, that sounds very complex, eventually translates into photons being the mediators of an instantaneous all-to-all interaction between the emitters. So here I prepared a little experiment in which you typically prepare the array of emitters of with an initial state which is of interest, and then you let the system decay as a whole. So this produces a burst of light which you then collect, and there may or may not be some photons that get trapped between these emitters, and the system is behaving as a whole. However, there is an increasing number of experimental platforms that shows that this approximation is no longer suitable. The main observation that they are doing is that photons actually need some time to get from one emitter to the other. This is a problem that we're going to be tackling. And here I prepared a little animation to illustrate what I mean. And it's that when you start the system, photons actually require some time to travel from one place to the other, and this affects the dynamics. We expect the emitters to decay and to experience revivals, and these revivals will depend on the properties of the photons that are produced. And we will later see that we can play with some extra parameters in order to tune the dynamics. I'm a theoretical physicist, which means that I'm constantly facing the same challenge, and it's not boring my audience with math. So I'm going to be running a little bit through the derivation without entering into the details. Are going to need to have a faith in me. But yeah, of course, the first step is always to consider a Hamiltonian to describe this system, and it's the one that you can see in the slides. It's very amicable and very usual in this type of systems. We essentially have three contributions. The first one is the energy of the excited state of the emitters. The second one is the energy of the photons, and then there is an interaction between the emitters and the photons. Notice that for the operators representing the emitters, we're using the letter S, which is a very uncommon choice. This is because we want to remain general as to what type of emitters we're using. We will later see that by fixing the algebra of these operators, we can either choose to have a differential equation for two-level systems or bosons. Now, without entering into a lot of detail, I will tell you that we want to derive the set of Heisenberg-Langevin equations for the operators of our emitters. The way we do this, for those of you who might be familiar, is with a Bickner-Weisskopf type of treatment. We essentially, is this working? Yeah. We essentially derive the differential equation using the Heisenberg equation for the operator S, the differential equator for the operator annihilation, and we can formally integrate the equation for this operator and insert it into the differential equator for the operator of the emitter. A lot of words. This essentially leads us to this differential equation, which have two important contributions. This first one, which we can interpret it as quantum noise, and is proportional to the annihilation operators in the initial state. And a second term, which is perhaps the most interesting one, because it's an effective interaction between different emitters, and is weighed by these memory functions, which have a central role in the methodology we have developed. And this term right here is a commutation relation between the operators of the emitters. One of the reasons why we don't usually work with Heisenberg equations in open systems is because when we have the degrees of freedom of the electromagnetic field, these guys right here, our operators belong to an infinite dimensional Hilbert space, which means that they are represented by infinite dimensional matrices, which of course are very hard to compute. However, if we are able to neglect this term and preserve the effective interaction, what we get is a differential equation which is closed in the sub-Hilbert space of the emitters, which is the ones we're interested in. So what we're going to do is precisely that. We're going to drop the quantum noise and see what happens. Now we're going to be considering two types of emitters, linear emitters and two-level systems. For linear emitters, it so happens that there is a strategy which allows us to remove this guy exactly, meaning that there is no approximation needed. However, this is not the case for two-level systems. But as we will later see, we can drop this quantum noise and consider this an approximation, and we will see that it is, in fact, a very good approximation. Now that the math is gone, I'm going to show you a little bit of the results that we found. We performed a numerical integration and compared the results with some established methods. For two-level emitters, which are qubits, we have these two graphs showing a very good agreement, and we compared it with a Bigner-Weisskopf method, which is an exact method. For the linear emitters, because we could actually get the analytical solution, we could use it to gauge our integrator in order to ensure that our solution has converged. Here, there is also an important parameter, which is gamma tau. This parameter represents how much have the qubits decayed when they start seeing each other, when photons can actually arrive from the neighboring emitters. When this value is very small, like in these cases, emitters are very close, so we are very close to the Markovian case. However, as we increase this parameter, the emitters are separated, and we experience the decays and revivals that I showed you in the animation. Just as a quick comment, by tuning the distance, we can also generate bound states like the ones we're seeing here, in which the qubits do not fully decay, but this is not the case in general. This is why we have a parameter that is a multiple of pi. Once we establish the validity of our method, we wanted to use it to uncover some new physics, which is what we did. One of the first things we observed is that we could either enhance or suppress the emission of our emitters by tuning the optical length of the photons once they travel between the neighboring emitters. Here, this guys represents two-level systems, and these guys represents cavities. And we can see that in both cases, we were able to go over or beyond the normal decay, which is represented by this black dotted line. Also, another effect that was a little bit trivial but unexpected for us is that we are sort of breaking asymmetry, because when the interaction is instantaneous and all the emitters are formally equivalent. However, this is not the case when we introduce delays, because as the dynamic starts, this emitter is only able to interact with his first neighbor, while the emitter in the middle of the chain is able to interact with both of them. This is why we see a difference in the behavior of the emitters of the chain. The next thing we do is observe how the superradiance behaves when we introduce delays. For those of you who don't know this phenomena, this is a well-established result from, I think it was Dick, that when emitters interact with each other, they present an emission that is enhanced because they have collective behavior. This is not the case for bosons. Here in the vertical axis, we can control the distance between emitters and therefore the non-Markovianity. And we did the same for bosons. And what we observe is that, in fact, superradiance emerges, but not with twice the time a photon takes to go back and forth in the chain, but once, suggesting that this emitters get correlated instantaneously when they are able to see each other. So as a take-home message, I wanted to highlight some key points. We have found an alternative approach that, while it's an approximation, it's extremely precise and allows us to simulate systems in this non-Markovian regime. These tools uncover new physics, like, for instance, the cascaded superradiance. And this method, I want also to highlight that it's particularly simple, because other methods that exist require tensor network algorithms, which are very hard to do. Our numerical integrator would only use a couple hundred of lines. And as a teaser, a little bit of commenting on the works we're developing now is that by making some small changes in the memory functions, we're actually able to cover a wide variety of waveguides. For instance, ring waveguides, or waveguides that are closed. And then we can use the fact that we don't really care about the number of excitations to put covering drivings on the emitters. This allows us to study stationary states that are non-trivial. And that would be all. If you have any questions, feel free to ask me.
Okay, thanks for a nice talk. Any questions?
Thank you for your talk. Could you please comment on superradiance? I saw, like, in the plots which you show, like, there are some discontinuity, I would say, like these steps. Like, what do they correspond to?
Yeah, these steps happen because photons actually have a delay. As you can see in the graph here, we are collecting the burst of light that is produced by one of the ends, which means that photons need some time to arrive here. Photons that coming from this emitter arrive instantaneously, but they have a delay coming from here, 2 tau, 3 tau, etc., which is why we see this escalated behavior, which is what we found was new.
Thank you.
Any more questions? If not, I have one. Did you assume that your waveguides don't have any loss? Or, I mean, well, the question is more like this method can be applied to lossy media or more complex media.
I mean, perhaps I didn't mention it, but we're treating with an open waveguide, which means that the ends are open, so photons are actually abandoning the system, which means that this can be modeled as a loss. But yes, of course, we can include more loss in between emitters. We didn't do it, but we could.
Okay, thanks. So let's thank the speaker again.
¿Con PDF o con PowerPoint?
Creo que las manda con PDF.
Por mirar el tiempo.
So our next speaker is Thomas Levirati, and he's going to talk about photonic quantum gates and two-photon process in waveguide QED. So, Thomas.
Well, thank you very much, Blas, and thank you for all the organizers for organizing this nice event. And also thank you, Carlos, for doing such a nice introduction to waveguide QED. He had this good news today, so I don't have to introduce very much. Okay, so I will do a little bit of a resume of my thesis work about generating non-classical states of light and doing quantum gates with photons using waveguide QED. And one of the first questions could be why to do photonic quantum computation. And this, one of the principal reasons could be that photons do not interact in free space and in classical media. So basically, qubits stored in photonic states suffer from very low decoherence effects. And another reason is that in the paradigm of waveguide QED, single photon gates or single qubit gates are very easy to implement. For example, here we encode a photon as a flying qubit, in the sense that we have two waveguides. A photon present in one waveguide would be a 0, and a single photon present in the other waveguide would be a 1. And we can do very easily an arbitrary qubit rotation in this paradigm, coupling a linear system like a resonator, cavity, or a beam splitter, depending if your waveguides are in the optical or microwave. So a resonator will be in the microwave, cavity will be in the optical. Basically, for example, here we compute the scattering of a single photon impinging in this cavity or resonator. And well, the transmission coefficients are about that, but we are assuming chiral transport. That means that the photon cannot reflect. This is one of the first issues, how to implement this chirality. But yeah, here you see that, for example, if the photon comes on resonant and the cavity is coupled equally to the waveguide above and the waveguide below, then you will have an X gate. And if you tune a little bit the couplings like there, you can show that you can implement a Hadamard gate. So this is very easy to implement single qubit gates. And it's all linear physics. But now, if you want to implement 2 qubit gates, there is a problem. And the problem is the same thing that we like about photons. That is that they don't have interactions. So in order to implement 2 qubit gates, we need some process, physical process, that makes photon-photon interactions. And for this, we need nonlinear systems, because the scattering for a linear system, like a cavity or a resonator, is just the product state. If we come with 2 photons impinging onto a cavity or a resonator, the output will be just the product state of single photon processes. And we don't, if we want to implement a control gate, some gate that can perform entanglement, we cannot be using a linear medium. So we need a non-linear medium. Like a 3-level system, or a 2-level system, or kernel nonlinearities, etc. Well, just to make an idea, this will be some encoding for a 2-photon gate. So you come with the blue waveguides are the photonic qubit A, and the red, the photonic qubit B. We can perform any single photon very easily, single photon gates. But then for the 2-photon gate, it's more complex, and we need some nonlinear video. And my 2 works, I will briefly wrap today, are about doing a control set gate. So we have another issue to make a control gate. That is, if we come with 2 photons onto a nonlinear system, we will get entangled states and correlations between the photons, but not necessarily those that we want. For example, if we just use a 2-level system and chirally coupled to 2 waveguides, and we come to 1 waveguide, for example, and we come with 2 photons, there will be an inelastic process in general. The scattering matrix is more or less that above. And basically, the idea is that the frequency of the photons shift because there is a continuum of scattering outputs possible that preserve total energy. So we will get with a very strange wave packet where there is a lot of components of different photons with different frequencies, and we basically will distort our nice Gaussian single photon wave packets that we came from. And we don't want that for quantum computation. So the third issue is frequency correlations, like distortion of the wave packet due to inelastic processes. Well, and this here, there is Zrinsky and Sorensen with the very nice proposal for avoiding this problem. And they use 3-level systems, and the two photons that come to the system are counter-propagating. One comes from the left, one comes from the right. And, well, they assume chirality, the idea that one transition will couple only to left propagating modes and one transition to right propagating ones. And they solve the problem about inelastic scattering, because there is very nice thing that I won't get into very much detail. That is that when you have a periodic array of emitters, you now not only have the conserved quantity of energy, but also a conserved quantity related to the periodicity of the array and the quasi-momentum of the polariton excitations, which are hybrid light matter excitations of the array. These polaritons are only emerge when you have an array of. So you need more than one system, more than one scatterer, so an array of 3-level system or 2-level system, in order to have this quasi-momentum conservation. And this imposition of another conserved quantity will suppress the inelastic scattering events, because all these events do not conserve quasi-momentum. Okay. Nice. So now I will talk a little bit about how we translated this, well, because the idea is that here, how can you get this chirality, one transition to chirally coupled to one to the left propagating and one transition to the right propagating? Well, the most clear idea would be to be in the optical, where the photons have a polarization, and you can have some kind of spin momentum locking and engineer this transition to have dipolar a dipolar polarization, and you can do something like that in the optical, but it's not clear how to do it in the microwave, where there is no polarization of the photons. And so we combine a little bit of here and there, and we use these giant atoms, which is the idea to couple an emitter known locally to the waveguide. So you have two coupling points, distance d, which if the photons travel group velocity in the waveguide v, then there is a time delay between the two legs. And basically you can imagine that if the emitter emits a photon, it can either emit it through the left leg or to the right leg. And so there will be a phase, there will be constructive or destructive interference if you tune this distance properly. And if you tune, especially you have to put a complex phase, because otherwise you don't break parity or chirality. You don't break chirality, so you could not have chirality if you don't put a complex phase. And doing this, you can engineer a momentum-dependent coupling, which for certain frequencies of the emitter cannot allow processes where the photon is emitted right or left. And then, well, the shape of this coupling depends with the frequency like that. And basically, you have now, and we use also a molecule. That means that we have a molecule of two emitters. And so in the single excitation subspace, you have two modes that are the symmetric superposition of the two emitters and the antisymmetric, which there is a splitting of these two modes with J. And so we have two resonance of this molecule, artificial molecule. And then if you place one resonance for the specific frequency that only couples to left propagatings, and the other resonance for the specific frequency that only couples to right, you can't emulate this system by Srinsky and Sorensen of a 3-level system. And then I won't get more into it because I don't have time. But the idea is that you replicate this system and you can get a CCA gate in microwave. And it works very good for only four molecules, and it's very nice. And also, you only need one molecule to be nonlinear, so you can replace one qubit with a resonator also. Very nice. And this, where here, we have the same, also a CZ gate, but now for topological waveguides, which appear in the edge of topological insulators. Also, if you are interested in this. And yeah, well, thank you very much. And any questions? These are my collaborators, Alejandro, Carlos, and Tomás. So thank you very much. Yeah.
Okay, thanks, Tomás. Any questions? A bit shy today. Nobody? So I have a question. Maybe I didn't understand part of the talk, but you said you are, well, you work with 2 photons, no? But you also said that you are working in the single excitation manifold or something like that. I mean, did you can...
Yeah, okay, thank you, Blas, for that question, because I didn't explain myself properly, probably. The idea is that you come with 2 photons on the waveguide, but you are interested in the single excitation subspace of the molecule. Because the idea is that you can only excite one of these 2 single excitation transitions. And due to the nonlinearity, all the 2 excitation energy levels of the molecule are suppressed because there is a huge nonlinearity, so you are not resonant anymore with these states. And so basically there is saturation effects. You can only excite once the molecule and the other photon passes by. And this way, due to saturation, you have a nonlinear phase. I didn't get too much into that. I'm sorry, but good question. Thank you.
Okay, so let's thank the speaker again, please. Okay. So. To pass the presentation with this and the laser is. Are you sure? Yeah. Thank you. Okay. So, our last speaker of the session is Janis Lefroy. I hope I pronounce this well. I'm sorry. And he actually talk about partial and Hayes maximal entanglement stabilization of the ice emitters. So.
Thank you very much. So thank you first, the organizer, for making everything possible here. And today I want to show you my work that I've been carrying with Carlos Sanchez Munoz for the last month, and which is basically trying to make entanglement between some emitters that work at few terahertz regime. So I want to start with a motivation, let's say, of why we want to use some terahertz hardware and why not microwave, let's say. And the motivation is this mess that I basically don't understand anything about this except the fact that you have to refrigerate through many steps to go to 10 millikelvin. And this is a problem with superconducting circuit, and that's why we have seen in some talk that people want to work in the optical, because with this you can remove most of the step and you can just refrigerate to few Kelvin or even work at room temperature. Now, when you work at optical, the problem is that you need to be super precise with your manufacturers. And then our proposal is to work in between, let's say, such that we don't need to design such complicated and such fine qubits, and at the same time don't need to refrigerate as much as the superconducting circuits. But let's go back to my work, and then I want to show you 2 first things. First, how people have been preparing entanglement using driven dissipative system in the optical, and then what are these turrets emitters. And basically our work is just mixing both and doing some entanglement preparation in the turrets. Okay, so first, what have been done, and this first paper of Alejandro González Tudela, which is a proposal of doing some driven dissipative entanglement in the optical. And basically he has two qubits, identical, coupled to waveguide with collective decay, and they have seen that they can prepare some entanglement, but to some extent. And this is a measure of how much entanglement we can make, and you see that they can achieve some 40% in the steady state, which is not perfect, but this is a first proposal. And then you have a second proposal of Peterzola group, whereas I've seen that if they detune this time the qubits, they can have this specific system, energy system here, and if they drive the qubit, they can isolate this antisymmetric state, which is already entangled. And they can also compute how much antisymmetric states they are preparing at the end and how much entanglement they are preparing. So this is basically it with the entanglement preparation, and now I want to talk about the turret emitters. So the big challenge is that for now I have an optical emitter, and all I have is this decay in the optical, and I want to make something that works in the few terahertz regime. So two things that we'll be talking about that come from this paper of people from Autonoma from here is how we open this terahertz transition, and then how we couple it with a cavity. So once again, I have my emitters, but this time I shine a laser on it. And what happened is that I open this ladder, and I have this E and G, my qubit levels, and N, my laser levels. And I have this detuning above between the qubit and the laser, and this drive omega L, which is the frequency of the laser. Now, if I assume that this is a wall and not something separate, I open this transition here, plus and minus, that will be now my qubit. And this is particularly interesting because this frequency of this dress qubit is now entirely modulable, and I can change it by modifying my detuning between the laser and the qubit and the Rabi frequency of the laser. Now we need to couple it to a cavity, and so you see this is basically the Hamiltonian of a cavity and a qubit that are coupled through this term in red and my optical drive, so my laser in blue here. I just expand the term, nothing changed, but the problem here is that the cavity is in the terahertz and my qubit and my laser is the optical. And what you can say with this is that they basically don't talk to each other, and it's as if the cavity and the qubit are not coupled because the frequencies are so far to each other. Now the solution to it is to use a permanent dipole moment. And by doing this, and if I add a permanent dipole moment to my equation, I expand it, I simplify by doing some rotating wave approximation, and I see that at the end I still have a coupling between the cavity and the emitter, which is given by this sigma z here. Now I want to sum up the two things that we have seen, so the dressed emitters and the cavity. And we see, and we see here that I end up with a coupling between the cavity and my dressed emitters that is that is given by this xi operator, which are the ladder operator of my dress qubits. So now that I've introduced everything, we can go into our results. And just to summarize what we need some detuned emitters that are driven and coupled to a cavity. The problem that we have still is that I indeed have an emitter coupled to a cavity, but which is not driven. And what we can do is add a second laser that is detuned from the first one, and that is detuned at the frequency of the dressed emitters. And this way I can retrieve this detuning between the emitters, this coupling, and this drive. And we can prepare some entanglement to some extent, of course. So here I prepare the antisymmetric state. And at the end, I was willing to optimize this process. So I have some easy tunable parameters, which are the drive of the effective drive of the qubit, the detuning between, so the difference between the qubit frequency and the frequency of the cavity, and how much, what is the dressing factor between, so how much laser or detuning are put into this dressed Rabi frequency. Some harder parameters to tune are, however, the cavity loss and the cavity coupling between the qubit and the cavity, because once you do it, once you prepare your system, you cannot change it. So now I want to optimize these easy tunable parameters by fixing this kappa in a chi, and I obtain this curve here, where this red cross is some cavity simulation done by people at Autonoma, and you see that they actually did a job that is too good, because they have too much coupling or they are too low loss rate, and if they were going to increase the loss rate of, or diminishing the coupling, you were having better concurrence. But this is still not really good result, because you see that they obtain 0.5 concurrence, or at best 60%. But if you are going to lower the frequency of the cavity, you can obtain close to 1 concurrence, or almost perfectly entangled state. So now the next step will be, instead of working in the cavity, working into the waveguides, and see maybe that you have some enhancements of the decay of the terahertz emitters, and then you would have long-range interaction between your emitters. Finally, I want to talk to other prospects and other motivation of using these terahertz emitters. The first one is you could create some warm-cut qubits. So instead of using superconducting circuit and working at 10 millikelvin, you could work at 10 Kelvin. And this is really interesting qubits, because these are non-trivial in the sense of quantum error correction. They're already protected by some symmetries. And the last one will be doing some time-dependent coupling using this system. And this is particularly interesting for distributed computing. So finally, I want to thank my my supervisors, Carlos Sanchez Munoz and Diego Martin Cano. And thank you very much for your attention.
Thanks, Dennis. Any questions? No one? So, okay. So, I wanted to ask you about a bit details of your work. How do you model the dissipative? I mean, are you using a Lindblad master equation? Yeah, okay.
You have to go through the master equation of free-space decay, and this way you can see that you have some optical mode of decay that is still the decay that you have still in orange here. You also have some decay in terahertz, but the problem is that since it's at way lower frequencies of your optical, the rate of the decay is neglectable compared to this optical decay, in free space at least. That's why in maybe waveguides you can have this decay rate in the terahertz that is more dominant, and then you can have, since it's lower frequency, it will be longer range, and then it's maybe interesting to work into this waveguide.
If nobody has another question, maybe I can, well, I have just, sorry. And you model the interactions between your emitters. Are you modeling them with, I mean, somehow? I mean, are you using the green function of the waveguide or something like that, or are just parameters? So, I mean the a bit later. Yeah, I think so. There, for example, that J, the coupling between the emitter 1 and the emitter 2, are you modeling it with the somehow?
Yeah. So this is not my work for now. This is work from Alejandro Vivas-Villaña, and he still get this coupling from the master equation when you get this collective decay of the qubit, and also this coupling when you work in free space, because we consider that this is still a cavity and not a waveguide. Once we consider a waveguide, indeed we have to consider the
the green function and how this propagates. But for now, this is considered to be free space.
Okay, so third speaker, please. So okay, we're done. So let's go get lunch.